Yeah. Good to see everybody. We have a special Monday seminar today. I wanted to give a little bit of background on why, in my view, we're doing this. You know, when I started in AMO, I remember when I was taught how to align things, never felt very formalized. Right? You want to figure out the focal length of a lens, hold it above a sheet of paper, see when you see the image of the light bulb, that's the focal length of the lens. You need to make sure it's far enough away though, right? So, right? You need to build some imaging system. It's kind of working when it images a point to a point. We can't tell the difference between a translation in our lens and a tilt in the lens, but the numerical aperture of the imaging system was garbage anyway. So those aberrations didn't mess anything up, none of it mattered. So that was like 2004. Fast forward to today, we have very complicated experiments. We have microscope objectives giving us single site resolution and imaging systems. We have very high finesse cavities where aberrations can mix modes and hurt our finesse. But we're still, for the most part, aligning optics like it was 2004 by sort of randomly searching in the parameter spaces. And these systems have gotten extremely complicated. So can you imagine that there are people who actually have thought deeply about aligning optics as a real research problem, right? And have developed tools to do it over many, many decades. So we've got Bob Parks here. He has a wonderful podcast that if you like crazy optics and alignment and all of this stuff, and even if you don't, even if you never want to think about it again, you should probably be good at it. So then you don't have to think about it anymore. Bob can tell you how to do it. And so, you know, he is on the faculty at the University of Arizona, College of Optical Sciences as a research professor. He has a proud tradition in the optics industry as well, going back to Eastman Kodak in the 60s. I don't know if you guys have heard of cameras, but they used to exist with film and they were a separate. Did any of you ever own a camera that was not your phone? Okay. You know, we'll take it. We're about to optics. Was it a film camera?
My birth year starts with 19.
Okay, there you go, 99.
97, thank you very much.
Touché. Anyway, so Bob has all kinds of experience in this area. He's got some very cool stories about using Bessel beams and using new types of microscopes to deterministically align imaging systems. And so I thought, given this current moment, it was the perfect time to have him through to share some of his perspective and tell us about the hardware that he's developed, this point sort of microscope. I would say Bob's schedule is not completely full, I don't think. And I think it's a very special opportunity to be able to talk to him, both for us and for the community at large, so that he can see our experiments and how hilariously and perhaps unnecessarily complicated they are, to learn more about the opportunities. So, no further ado.
Well, thank you, John, for the introduction. I'm really pleased for the invitation and delighted to be here. So, as I said, this is going to be a talk about optical alignment, but let me give you a little background here. We're trying to align things so that we maximize the performance of the system, get as much irradiance on the target as possible. I'm a little bit new to this laser experiment type of alignment. I'm started developing the PSM for dropping lenses in a tube for the people that do have film camera optics, and thinking about how to get lenses lined up in a tube. It wasn't until that Yaffe called me up a couple months ago and said, hey, we've got this tabletops full of optics. Can you align free space optics? And I just had never thought about it, but realizing it, that there's, yeah, great place to perhaps optimize things here. So then I'm going to talk about tools for alignment. This may be some of what I'm going to talk about is new to you, so I'm going to go into a little bit of the historical background about both autostigmatic microscopes and Bessel beams. Not that you're unfamiliar with Bessel beams, but I think you guys probably use them for tweezers and finding exoplanets and stuff. I've used much more mundane for just using them because they propagate through an optical system like an ABCD ray. It's a very sort of unexciting use, but very practical. Then I'd like to outline my approach to alignment and then show you how to actually use these tools to get things lined up. So I've sort of hinted at that already, but the importance of alignment, you know, with your modern optical software, design software, you got particular specs. The software is going to tell you the best design you can possibly do. There's little room for improvement there. Your optical components, you can make them essentially perfectly these days with the interferometric testing, CNC machines, that sort of thing. So the only thing you are left with to improve performance of an optical system is putting it together correctly, so that all the pieces are where your design said they ought to be. And in fact, you're not going to get the performance out of your design that you intended unless things are where they're supposed to be relative to the design. So that's what I'm thinking of in terms of alignment. The other thing is your image space or your alignment space is, well, three-dimensional, but at least in terms of the precision and angle. If I can do better, maybe I used to be able to do 10 seconds of arc alignment in X, 10 seconds in Y. I can do 5 seconds, but I can do it both directions, so you get a quadratic improvement in general in how much light you get on your target. And it was an example from astronomy that got this into my head because they do a lot of astronomy in Arizona. It had to do observing time. Your telescope's really well lined up. You can get the light in the slit of your spectrograph faster than if you got poor alignment. And people only have maybe 2 hours on the telescope on one night a year, so they better get all the data they possibly can. And so in the end, alignment comes down to money and time kind of thing. It's the better you do your alignment, the better progress you're going to have. So the two tools we're going to talk about is the autostigmatic microscope. It's nothing more really than an autocollimator. If you take the objective off, you've got collimated light coming on out of it. You put an objective on, you locate focus here in 3 degrees of freedom. It's a point in space. The way I've got it shown here is with a surface here, so light coming out, angle of incidence equals angle of reflection, the ray comes back. And so on the camera, you get an image that's completely or exactly conjugate to where your source is. And so when you get a cat's eye image here, and electronically set the centroid on that spot, it's essentially bore sighting a rifle scope. You know that the light coming back into this, if it's coming back in the middle of your crosshair, then it's coming back exactly on top of where it went out of the microscope.
Is it important that we know what an autocollimator is? That's my guess, it's that most of us.
Oh. An autocollimator, yes, is an ordinary autocollimator. You have a reticle back here that's illuminated, and an objective lens here, and then the light just keeps going out. If you put a plane mirror out here in space, and the reticle projects back to where it was when you set 0, you know that your plane mirror is perpendicular to the optical axis of the autocollimator. So it's a device to measure 2 angles or 2 degrees of freedom in angular space. People who have used an autocollimator, the most difficult part of using it is if you got a mirror on the other end of your lens bench. Just getting the light back in the autocollimator in the first place is the difficult part of the alignment. Once you can see a little bit of the reticle, you're essentially done. The reason autostigmatic microscopes are relatively unknown is to fish around and find this spot, you've got 3 degrees of freedom to find. And until lasers came along, you didn't have enough light to do that. And autostigmatic, well, you'll see a little bit in a slide or two, have been around an optic shop for 100 years to measure the radionic test plates. But you already know what the radius of the test plate is from mechanical spherometer measurement, so you know where to put your microscope in the first place. And you've got fixtures because you've been doing it over and over again, so you know approximately where to look for the image. And so you can, in an optics shop environment, pretty easily use this, but to use it more generally until you had a really bright light source, it was impractical, essentially.
You're gonna say more about light.
Yeah. Yeah, and John's comments here, if you've got a question, please put your hand up and we'll discuss it to clarify any points. If it's kind of really off subject, I'll suggest we talk it about offline. But yeah, if there's something you don't understand, please let me know. Yeah, this is a Bessel beam, or the intensity pattern you get from looking at a Bessel beam. And I'll talk a little bit more about the history and how we got here, why it's useful as well in the next slide or so. But first, I'm going to talk about the autostigmatic microscope. Just a bit of history. This is the earliest I've found in English-speaking literature about an autostigmatic microscope. And it's just interesting. The guy said, well, he couldn't find anything that told you how to find the radius of lenses in the literature. And so he devised this device. And it's essentially the same optical system that's in the current device. You've got light coming in from a distant source, so it's essentially collimated. An objective lens, which in our case is a microscope objective, when the light hits the convex surface at normal incidence, it then reflects back, goes through a lens to focus it, in his case, in the plane of an eyepiece, and then you observe where the light's coming back here. Likewise, if it goes through focus to concave surface here, that's how you find these surfaces in, or the center of curvature in 3 degrees of freedom. All these papers that I have mentioned here, if you would like an original, send me an email. I've got them on my computer somewhere. We can get you those. More recently, Professor Steele down in Australia worked for CSIRO, which is the NIST of Australia. He was interested in these things to measure the radii of contact lenses because they were, they were the standards people so Australian ophthalmic people needed to know what the radii of contact lenses were or have a method of measuring. Well, I should drop back a little bit and say, the paper there from Drysdale was English. If you had gone to Imperial College to study optics, you would have known what an autostigmatic microscope was. And in fact, I had an Australian astronomer walk by my booth 20 years ago, and he did a double take, came back, and he says, "You call that an autostigmatic microscope?" And at the time, I'd never heard the term. I always thought of what we had this point source microscope. And I said, "Yeah, I guess you could call it that." He says, "Good, I have an application. You'll get a PO when I get back to Australia." It's because of this English thing. I mean, there's a textbook, which I lent to somebody, and I don't know where it's gone to, written about 1936, where they have a page or two talking about autostigmatic microscopes, part of the curriculum at Imperial College. In the US, for some reason, nobody knows about these things. On the other hand, Warren Smith's book, which I find the most useful single, you guys talk about being optical or being physicists, not optical engineers. If you want to know practical optical engineering, I would say this is the best single reference. There's much newer additions to this, but Warren Smith's book is great at this cover optical engineering in general. But in any case, he says, essentially, this autostigmatic microscope is good for finding backfocal imaging lenses. Whoops. Let me tell you a little bit about myself and my involvement with alignment. When I got my master's, my advisor said, "Do you know how to line up end mirrors on a laser cavity with non-polymer?" And I had a good lab training in undergraduate school and said, "Yeah, this is great. Go for 9 o'clock tomorrow morning and we'll get going." Well, I hadn't really planned on being in optics at that point, but that's how I got started in optics. And so I've had this association with alignment ever since. And then my first paying job was at Kodak. The very first job they had me doing was using, I don't even remember what they called it, but an autostigmatic microscope to measure the radii of test plates. So yeah, from the first time I got a paycheck, I was using an autostigmatic microscope. Later on, I went to work for Frank Cook, who made optics. I learned how you actually grind and polish optics. I never call myself an optician, but I know how to use the equipment. One of the things they made were hyperhemispherical domes. And one of the specs was to make sure that the two surfaces on the dome were concentric. Well, you could do it mechanically, but that's an extremely tedious, hardware intensive thing to do. The guy who was the chief metrologist there built this eyepiece where he took a optical fiber preform, drew it out and bent it in just an alcohol flame and put it in this eyepiece so that when you had the fiber at the center of curvature of those concentric domes or surfaces in the dome, if the two spots from the two surfaces came back on top of each other, you know you had the concentricity. And with a filer eyepiece in there, you could tell how far they were misaligned. So extremely easy to do optically where mechanically it's been very difficult. I went in to run the optic shop at Optical Sciences at University of Arizona and found that you could buy a commercial eyepiece from EG&G that had fiber built into it. They used on a spectrometer. I went to order a second one and couldn't because the craftsmen who used to build them had retired. They were no longer available. But by this time I had enough experience with using this kind of thing and saw how valuable it was. And that led to us building our own standalone device. And the very first commercial one we used was this little thing here that was small enough to put on the RAM of a coordinate measuring machine. So all these people needed to do was get the centers of curvature of all the lenses. Some of them were toroidal, some mirrors, but they all just needed to be on a straight line. And it essentially cut the assembly time by about a factor of 10, and they got better performance out of the system when they were through. So this is the current DSM. I've got one in my briefcase, so if anyone wants to see the real hardware, I call it out. We've got our point source, goes down through a microscope objective, comes back through the tube lens onto your CCD camera here. In addition, we've got a full field color illumination source, so the thing images as well. So if you want to look at a particular place in the field of view to get your laser lined up with that thing in this field of view, you can do that. And the full field and the point source are parfocal, this same plane.
All right. That's the distinction. So one of them is focused down and the other one's collimated coming in?
Well, it just illuminates the entire field of view of the camera. So
So that you can see the object on the
Yes.
camera.
Yeah, I mean, if it's paper, you can see the grains of the paper or whatever, or a CCD, you can see the pixels in that.
It's allows you to focus.
Yeah. And the beauty is too, I guess I'll go up here. We have a laser diode inside that's fiber coupled into here. There's a storage place here. So if you want to bring in a different wavelength, different power laser, it's just fiber coupled. You need an angle polished patch cord. You know, the connector has to be that angle polished instead of plain polish, but otherwise you can change wavelength or whatever. But the beauty is, because of the way we set the electronic crosshair, you know, when you point your laser on something, that the spot's going to come out exactly where, or it's going to come out in the middle of the cross. You can, to a micron or so, know where the laser is going to hit whatever you're looking at. And then any infinity corrected microscope objective will work. I usually use 10x because, at least in my lab, I don't think things on vibration tables. It's just senseless to use a higher power objective. But if you want to put 100x objective on, no big deal.
Then I find the center of focus with respect to the focal point. Is that correct?
Yes. Yes. And we also use it as a Bessel beam. You know, as we project a Bessel beam into it, we see it again. We want to get it in the crosshair. You can see here, I've just done this for illustration. If you had a convex surface here, you'll get your spot back, but it's essentially, you know, the same optical system in a Feynman green interferometer. If you wanted to get fringes off of this surface, you could. The only difference is the reference mirror in your Feynman green. We don't have a reference mirror here. We just use a beam dump to get rid of that light. But otherwise, it's essentially the same optical system. Now, when we first started doing this, I remember I told you about lining up all these centers of curvature on a line. The main thing we wanted to do, I thought the main purpose was to tie centers of curvature, for example, that you can't touch. I mean, you know they're there, but tactily you can't touch them. To tie them down to things that you can touch. And so, for example, if you want to put the center of curvature this near at a very specific spot, you can locate that spot in space in the wall, which represents a point, align your PSM to the ball, take the ball away, and now align the mirror in 3 degrees of freedom to that point. And my kinematic mount is nothing more than the lens post turned upside down with that sort of conical seat. And of course, you can do it the other way around. If you know you've got a mirror that's you want to use as a reference, find its center of curvature with a PSM, bring a ball in, align the ball then to that focus, and now you can measure where that center of curvature is. And so this is what I thought of in terms of its use, but it's obviously got many more uses as I've gotten familiar with the thing. This just has to do with the whole idea of how do you set the electronic crosshair. If you're using it as an autocollimator with no objective, you have a corner cube out here. Use that to centroid on the spot, which will then be exactly conjugate with the source, or it's the autostigmatic microscope with the objective. Again, focus on a surface here. The bright spot on the surface here gets relayed back to here, but that bright spot is conjugate with this, so that's why you set the cross. And you can do that, at least with a 10x objective, and know you're centered to 2 or 3/10 of a micron.
So for the one on the left, what kind of range do we have there? With the distance of the range?
Certainly across the room, yeah.
And then for the one on the right,
Well,
focus, there's
again,
one for spherical lens.
I've done at least as far as across the room.
I see, you don't worry about the fact that the lens doesn't subtend the full angle. So you're losing a
You
lot of
need more
power.
light, or yeah, you may have to bring an external source. Well, that's the other thing. The reason the laser diode is less than a milliwatt, so I can keep it a class 1 laser device. But if you want more power, then it's really somebody else's problem about the laser safety. You just, you're bringing in a Thorlab source.
But so you can plug a fiber in there?
Yeah.
Yeah.
Yeah, to go back. Yeah, you simply take this out. There's a storage place for this right next to that.
I see, the point is that laser source, that's not an auxiliary one, that's the main source. You just
That's-
unplug that and plug your own.
Yes.
What's the most power?
I don't know.
But there's nothing super sensitive inside, you put in like 50 or 100 watts.
Okay. Yeah,
So I was wondering, you kind of showed how to align like one surface to a point. Now, if I want to like co-center like a bunch of lenses, how would I do that?
I've got sort of a hearing.
Oh, so you have showed how to reference like one curved surface to a point. But now if I want to align like a whole train of lenses concentrically, how do you do that with
We're
those?
going to get to that. Patience. But that's where the talk's going.
Actually, I have one other question. You talk about like explain, you can switch out the microscope objective. Right, you're talking about, does the Z distance though between the tube lens and the microscope objective, is that like, that has to be aligned since not really?
To first order the making.
So it's the way that I should think about that the focal point is referenced to the focus of the microscope objective. So if the microscope objective is slightly misaligned, doesn't matter because that just changes where the focal point is that we're defining.
Yeah, and in fact, this is why you want to go back and do the electronic setting of the crosshair, because every time you screw in and out the objective, that bore sighting changes by maybe 5 microns.
So how do you do that?
You just put a surface here. It brings the spot back onto the camera, and you click the set reference to just some sort of. You just read bore sight.
And the statement is that the tilt doesn't matter. So all you have to do is find the place where you get a sharp focus, and then you're good.
Well, in fact, I often do this off of a steel ball. People say, well, that's spherical surface. Well, but it doesn't matter because light essentially is a 3 micron spot at that point. And so the fact that it's curved doesn't make any difference. You're still, if you're not normal to the surface at that point, it starts being, but it doesn't matter. As long as it's specular, reasonably speculative surface, you can foresight the thing. Now, I can talk forever, and I know we'll run out of time eventually, so I better get going here. Bessel beams, they've been around. Van Heel was doing these prior to, he was in the 50s doing this. But the thing to notice is the brighter core from the Bessel beam. He was using grooves millimeter wide to make his Bessel beams. About the same time, John McLeod at Kodak invented the Axicon. And the purpose of this picture is to show that whether you're located here and the light's reflecting back, or you're down here and the light's reflecting back, anywhere along this line, you can find that axis. And so you've got a finite distance that you know where the axis is for light. And then McLeod said, well, geez, if I want longer than that, I can put a concave back on Axicon, and now I can go meters for hundreds of meters. And that's kind of why we use a point source to illuminate the gradient, and I'll get to that in a slide or two. Those papers were back in the 60s. Jernin, it wasn't until 1986 or so, he published and called the beams that these guys were producing Bessel beams. And Jernin, in fact, used an annulus for creating the Bessel beam, but it's the same basic thing. And just this is data I took. This is theoretical data. Jernin, Gaussian beam here relative to, and I don't know what the how we normalize things. Quad cells don't work with beams with the Bessel because you've got the energy spread out, and so the quad cell is essentially insensitive to moving across. On the other hand, with digital camera, works beautifully. Very easy to centroid on it.
People know what quad cells are. This is a quadrant photodetector for photodiodes, and you take the thickness of the right to the left to figure out your offset.
They work great for laser beams, but Bessel beams, that doesn't work. Very shortly after Jernin, some Finnish authors, I can't find my reference, created Bessel beams using the grating. This picture here is the grating I tend to use, 50 line pairs per millimeter, just chrome on glass. We do illuminate with a point source. This is the only paper I've been able to find that talks about the difference. The red line is the core of the beam intensity if you illuminate with collimated light. This is if you illuminate with point source or spherical wavefront. The graph is misleading because it's normalized. This Z max would be way out here somewhere, if you illuminate with the point source. In fact, I'd say the people at CERN are lining up magnets on their accelerator hundreds of meters away from Bessel. And it's also less affected by atmospheric turbulence than just a laser beam. To create the beam, the fiber source hits the grating. It diffracts both plus and minus, so you get these overlapping wavefronts that appear to be coming from virtual sources that are centered either side of the where you put your fiber. But in fact, this is just two-dimensional. The whole thing rotates, so you essentially your source looks like an annulus after it's gone through the grating. Or if you're looking back into the grating, it appears that the source is an annulus. The other beauty of this, it's a plane mirror. In the zero order, you can use it as a plane mirror, but it has a defined axis. So it defines 5 degrees of freedom. I mean, it's a plane mirror that defines 5 degrees of freedom. And that this annulus thinks a little bit like zygotes bringing fire to do something about coherence effects of their interferometer. It's the same basic idea. So in our alignment, to get on with your question, we use the Bessel beam as a reference axis because it propagates through optical systems like an ABCD ray. In my lab, I was playing around with the thing. I didn't know anything about Bessel beams. But when I was looking at lenses and stuff, it said, I'm getting behavior like this is just a single ray. So went back with some students in optical sciences, went through the thing, did physical ray tracing, CMAX, the whole thing. Yes, it really does behave like a single ray trace program.
So what does that mean? Does that mean that core doesn't diverge much when you reflect off of that?
Right, and that you can find the principal plane in a lens, the micron or so, because as you scan the Bessel beam across the lens, you're focused at the principal plane, the ray doesn't move. You go a micron or two either side, the ray will move a little bit, but yeah, and so if you move the lens a little bit, yeah, the ray goes off at an angle, and you can get incredible angular sensitivity because you can get way away from your lens. So it is, I tell people it's a little bit like magic because if you use the sort of classical alignment, it makes things so easy relative to what you've been doing. The other beauty is, if you're way misaligned, you still have these rings to tell you which way to go into London. And with the grading I've used with the 15 line pairs per millimeter, we get about a 7 micron full width half max. The core is about 10 times more intense than the first ring. Actually, though, each ring has the same energy and as the core. And it's easy to create these gradings.
How big is the set of rings?
Do you translate?
He was asking how big is the easily visible rings?
Oh. Well, just the other day, we're setting up somewhere in the objective and the grading were misaligned. It's gotta be 3 millimeters. Well, how far, I don't know, but gross. I mean, this alignment's easy enough to see with your eye. You can still move things into place. This slide's to kind of show what happens both in transmission and reflection. The blue line here is normal to the grating and goes through the very center of the pattern. If my fiber doesn't lie on that normal to the center of the pattern, the spherical wavefront coming from it creates a reflected Bessel beam that comes back exactly on the opposite side of that reference. The transmitted Bessel beam is on a line that's in line with your fiber source. What I'm going to show you for doing the alignment, I use a Bessel beam created by one source as my reference axis, and I look at it in the other direction with the PSM. So I want to make sure my transmitted Bessel beam is actually lying on this reference axis, normal to grating. So what I do is put the PSM on this side of the grating. When I get the reflected beam right back in the middle of my crosshair, I know my source is on the normal to the center of the grating. Then I come over here to do the transmitted part and move the source until again it comes back on the crosshair. Then I know the transmitted and reflected beams are coaxial. And then the transmitted beam, because you're always the same distance from the grating, doesn't matter where the microscope is. You can still see the beam. Where if you do it in reflection, the farther you get your microscope away, the light spreads out and get less and less light back from the grating. Just one more physical or historical note. Conrad, back in 1919, and Conrad is the Imperial College lens design guy that I don't know if you guys know Rudolph Kingsley was the Rochester guy who was Conrad's student, and Kingslake's wife was Conrad's daughter. It's all Rochester stuff. But anyways, Conrad said, no, real lens systems have been put together, really has an optical axis that looks like in your CMAX program where everything's lined up perfectly on the screen. The centers of curvature are small distance from the intended axis and kind of scattered around. I'm going to show a slide on how we can determine exactly where that unique optical axis of an assembled system is. Okay, we'll get to the alignment. And I'm gonna, because I don't have much time, keep going fast here. But to define an axis, we need a line, we need 2 points, or make it a vector. We'll talk about how we create the 2 points, how we actually do the alignment. For the purposes of this, I'm going to say alignment's making the optical axis of our lens or whatever coaxial with the reference axis. And here I've said this black line from A to B is my reference axis, whereas the optical axis of my lens element is the line joining the centers of curvature of those two surfaces. And since it joins the centers of curvature, if I have light going exactly along the optical axis, the light intersects both surfaces with normal incidence. So there's no refraction along that ray. On the other hand, if you got a ray coming in parallel to your reference axis, goes through the center of the lens with the nodal point, that ray is going to continue on to be this, it come to focus, same distance above the reference axis is the center of lens is above the reference axis. What you want to do is tilt and decenter till you get both centers of curvature on this axis. Oh, and I should say this what I call optical center of curvature. The physical center of curvature is here, but if I'm looking into the microscope this way, because of refraction at this surface, the center of curvature of this surface appears as though it's here at a shorter distance than the physical center of curvature. That's why I call this the optical center of curvature. It's what you can observe with the autostigmatic microscope. And so the and this slide's kind of out of order. Let me go one more. So before we put the lens in, we line up the microscope so its focus is right here at the center or optical center of curvature of this surface. I put my microscope here. It's observing just what light's doing in this plane. So it's in a position where it can see the center of curvature of this surface. The Bessel beam just keeps going forever, so I can also see the Bessel beam. And so this gives you an idea. We've got the two light sources, Bessel beam here, but from the internal light source of the PSM, its focus here, I see a spot from this surface coming back. And so on your monitor, PSM, you've got your reference crosshair, you've got one spot coming from the optical center of curvature, you've got a second spot coming from the TV and Bessel beam. So now we've got two spots, but we know position and, or enough information to know position and angle of the centration of this lens. And the whole idea now is to tilt and decenter the lens until you get both of these spots centered on the cross. This is another, there are two ways of doing this, but this is the beauty of having separate light sources because we can electronically center on the cross, but if you get both spots on the cross at the same time, they get mixed up. But if you can turn one source off, you can electronically center to a couple tenths of a micron. Turn the other source on, again, a couple tenths of a micron to get the two on top of each other.
We have reflections on both surfaces.
But this is going to be way somewhere else. And in fact, you don't have to be more than 10 microns or so best focus. You can't see the focus. I mean, the straight light in the PSM is good enough that you've got to be, just because your light intensity falls off, it's the square of being out of focus.
Got it. So this is saying the other center of curvature is
It's somewhere, but
the
it's
side or something.
yeah.
So the light's reflecting back, but you just see it.
Right.
Is there like a Fourier filter or something? Yes. You're still collecting that place.
Let me keep going because I want to, but the whole idea here, there are a couple other things I want to get to before we finish up. So this kind of makes sense. All right. Oh, and then to your question. Once you've done this and you get both spots on the crosshair, things look exactly like they did before you ever put the lens in there. So now you can simply move back, use your Bessel beam as still your reference, and simply go back to the center of curvature, the next element you want to put in. And just keep doing that. Yes.
Is the point source microscope generating the Bessel beams, or do you have like, are there?
So I'm separately generating it in the next slide. I'm generating the Bessel beam here. This is PSM. It's got its own internal source. I think it's a Plano convex lens here.
So I should think of this as the Bessel beam defines the axis to which I want to align all of my lenses. Is that correct?
When you first have to align the point source microscope to the Bessel beam,
Yes.
and then you get a reflection from the source from the point source microscope and a transition to the Bessel beam.
Yeah, those are your two spots of light that you see on, or the cameras. Another thing, let me just go back a second. Remember I said you've got to line this up ahead of time using a cat's eye reflection? If you can't get both these spots to be in the center of the crosshair, no matter which knobs you turn, you know that you haven't foresighted the thing in the first place. I mean, I've had that situation where I've forgotten to foresight to begin with. I said, what's wrong here? I can't get both spots on my crosshair. Well, I go back and put something at the focus and eject and say, oh, I wasn't foresighted. So you kind of got a built-in guide to whether your setup is correctly set up in the first place. Here then is the example, just say a 3-to-1 beam expander. I've moved the PSM back so that I can now line up the second lens. Can you just keep marching down one after the other? It converges. I did this on CMAX. You've got to do a first decenter, then tilt. But the tilt throws the decenter a little bit off. So you've got to correct it. So you have to, because you can't, or most mechanical stuff doesn't let you rotate about the points you most like to for optimal. And that's why it's either just it's practical hardware constraint. This graph is some that alignment where I've done the first corrected the Bessel beam that improved the optical center of curvature somewhat. And I centered the optical center of curvature, which misaligned the Bessel beam, and so on. But it gets to, and this is log of microns. So I'm down here to sub 1 micron alignment at this point. It took me much longer to do the simulation than it did to actually. So. Now you could say I'm not very good at simulating, but, and this is the sorts of precision you can get with the 10x objective. And as long as your optical center of curvature stays 50 millimeters away, and you can measure to the half micron, you're down to this bar type of line. This just shows that you could set the PSM up on a 5-axis mount. So you've got the light coming out this way at what I call right angle adapter, so that the screws on the tip tilt change the angle in the right direction to make things work. The reason I want to show this is in this adapter, I can put what we call a multi-focus lens. But we just got a provisional patent on this. You say, well, what else is new? I don't know, maybe it'll go, maybe it won't. But this is the multi-focus lens. It lets some light come through because the PSM I'm using is an auto-collimator. So some light comes straight through collimated, some comes through a focus. So if you've got a 4x system, you can line up the elements in it without ever having to move any of the apparatus you're using to measure the alignment. In each step of putting these lenses, and whatever you want to put in the Fourier plane, you don't have to touch either the PSM or your end mirror. And part of what I've seen up at your lab, I would say some of the things you ought to be doing is making subsystems of different components. And so as a little subsystem, it's all sort of realigned before you set it on your grid plane. And then you've got a way of making sure within that little subsystem, everything's lined up. And then you can treat it as a whole optical system where I'll show you, you can find the axis. Yeah, this is the slide. Here I've got a hook triplet. But I've got my multi-focus lens. Part of the light comes out collimated, but I have two different foci where it focuses in two different places. You'd say, well, I do this. If ordinarily I get object and image on top of each other and auto collimate on the flat. But now it comes back to just one point, and so I don't know anything about angle. I know where that point of auto reflection is, but that's only 3 degrees of freedom. I need to go 5. By separating object and image and getting this plane mirror square with so that it's on the axis of where these 2 points are as well, I can uniquely define where the optical axis by sub assembly is, because there's only one place in space it'll exactly get the light coming back.
Sorry, for the plane mirror, for the whole optics.
Well, I didn't under.
For the plane mirror, I would think that
But I mean, I'm setting
you can
my.
at least translate it laterally.
Well, I set the plane mirror up ahead of time, so it's square with the auto column. And then I drop this in and look for these 2 places. And it can, there's only one place to space that length assembly B and still. Oh, there's only one place and still have the spots for that. Finally.
So you don't need the vessel for this.
Right, well, in fact, what this does. This fully focused lens could incorporate the Bessel beam grading, so that you've got then your autostigmatic microscope defines 5 degrees of freedom all by itself. You've got the practical problem that if you want to control the 2 light sources independently, so there are just maybe some practicalities in that. But the PFM by itself could be a degree of freedom device. This just shows about lining up parabola. That if you've got 2 foci and they got to be correct for the particular parabola you want. From one focus, you bounce off the mirror, come up to the plane mirror at normal incidence. The other focus, you're coming in and coming back to your parabola at normal incidence. So you can line up your parabola simply using its focus. I mean, the two conjugate points, you don't have to use the operations to line up the parabola. And obviously, if you use your imagination, you can get rid of half of this, and it's a way of lining up all parabolas without needing to look for everything. And if you can get these 2 points to a micron or so, you're doing better than you could using preparation. And I think I'm done. And I appreciate your attention.
I know we got a lot of questions during, so. If there are more, that's great. People, it's on the hour, so feel free to head out if you gotta go. So,
What would happen if you add back in the reference mirror where you got this? Would you turn this also into like a mirror, quickly sensitive? Because with like some alignments, micron is pretty good, but like sometimes we see that we're actually like more sensitive. Especially like if you're like overlapping spots, I mean, everyone knows when you're fiber coupling, it's okay to overlap spots, but like to get it really down, like interferometric, it's hard to beat.
Yeah, well, where I have said a couple tenths of a micron, it's with a 10x objective. I mean, and for my lab where I don't have vibration tables and all that, but You can put a 100x objective on here. Yeah, any infinity corrected, non-cover glass type objective will work. So you've got potential that potential sensitivity. And in fact, I mean, one of the questions people recently asked me is, how do you align tube lens with an objective? Well, I was kind of amazed I have a cheap 100x objective. Yeah, it's pretty easy. Well, the flange on the objective gets rid of the tilt. The threads still have maybe a 5 micron slot every time you screw it out, and I can see that. And with a 100x objective, that moves return spot. Again, too, the Bessel beam makes it easy to find. I mean, you'd be searching forever to find the. I mean, if you just put a point of light at the focus of the objective, you want to know where it is at the tube lens, that'd be hard to find. But if you shine a Bessel beam in there,
I have a question about the aligning of lens systems. So for when you're using the PSF to align the lens system, do you need the planar mirror in order to get the back reflection on the PSF? Or do you always need to put a planar mirror after your lens?
So you,
oh no, you can. You've got to use ABCD optics or something to figure out where you're going to see a center of curvature.
I guess I was just thinking if so if I have my PSF and it's sending the beam out to this lens, if the lens's AR coding is so good that there's no back reflection on the lens itself, do
okay.
you always need this planar mirror after the lens in order to get a difference?
Well, you
I
can
see.
use a different wavelength, and I have yet to find a lens where I couldn't see reflection. I won't say it's been easy,
Yeah.
but I haven't found a coding yet where I haven't been able to.
that's why we can go up to 100 milliwatts.
Or, yeah, probably the easier way is, like you say, you just use a different wavelength, but, yeah.
So I think I'm noticing that kind of if you want to try to be very methodical, kind of building up kind of de novo, like a very well-aligned optical system, you really want a lot of degrees of freedom to kind of, you want a lot of knobs on each lens. I guess kind of in our experience, we think this extra tunability kind of comes at a cost, both to like the ultimate kind of stability of the final setup, how often you need to retouch it, and as well as kind of also a cost of compactness, kind of all these knobs actually just take up space on the table.
No, you bring up a very good point, and, you know, if you're putting lenses in the tube, things are kind of constrained by the seats. You don't have the 5 degrees of freedom. You need to get complete alignment. You guys do have 5 knobs you can turn, but I agree that you don't necessarily want all 5.
Yeah, oftentimes we don't.
But you could imagine a scenario where you're building this once, you put your lens on a 5-axis translator, and then torsil it in its housing in place. And then, but like the way we do counts, or the way we align the collimators on laser diodes back before everyone just bought them.
Yeah, and in fact, that laser scanner example I gave at the beginning, that's what the people did. They shimmed and used UV cement to lock the lens into their mounting elements. That makes sense. Yeah.
We often use sort of low-cost lenses from,
Like,
we often use low-cost lenses from the standard suppliers, Gorlab and things like that. The lenses are not always perfect. The curvatures may not be aligned with each other. So,
oh, but, well, the radii curvature are always aligned with each other. They may not be aligned with the periphery of the lens.
so my point is, you know, how often do I have to diagnose the lens, the sort of standard parts that I buy? And I can see that you could do that with your instrument. Try to find the imperfection of the lens, but
Yeah, what if the lens has a little bit of astigmatism? Let's start with that.
For example, or
Well, this is one of the, I didn't talk about this, but because we send out essentially a perfect wavefront. I would guess 20th wave or so to down. If you've got as much as a tenth of a wave, to down again. You could see it in the symmetry of the return spot.
I see, you say you literally can't align better than that anyway. So,
Yeah, I mean, I had a customer, guess somebody from Denver or from NOAA, who bought a PSM, called up, oh, I'm happy, I think there's something wrong. And he was, had the lens and then a plane mirror, he was auto-calling a plane mirror. So I could see this sort of line image, something's wrong with the PSM. Well, thankfully, he sent me a picture of his test setup. I said, well, have you looked just whether your plane mirror is really flat? He said, oh, what that? It went back and yes, that was the problem. The plane mirror, the setup was the problem. I had another guy who we had a fairly large mirror, a long radius, but a mechanical mount with 3 screws to hold it into place. And I said, Gary, you tightened the screws too much. I said, come here and look at the image. You know, you could see 3 flares, and you could tell just for his body language, he saw, yeah, that's the problem. So it's, the other thing is, you know, talk about using it as auto collimator. Because we illuminate with a point source, you can see aberrations from the auto collimator. I mean, if what you're looking at isn't flat, you'll know that it's flat, or it's got a curve. The spot coming back won't be in good focus. Where ordinary autocollimators that project a reticle, the reticle may look fuzzy, but you don't know why. With the PSM, because of the point source illumination, you can sort of diagnose it wrong.
so the real upshot is if we take this approach, we're gonna have to buy better optics. Immediately discover that all of our.
Well, they're actually amazingly good. By and large. I mean, they may be somebody standard, but to your points, you've got 2 spheres. There is only one optical axis. May not line up with the periphery of the lens, but there's only one optical axis.
Okay, so let's thank Bob again.